we derived this element stiffness matrix for trusses, just for you to recall that this is the element stiffness matrix for truss problems. It's a 4x4 matrix. We derived this and we applied this for each element, and then we create the global stiffness matrix. And we also found stress formula for elements of a truss to be given by this E over L and this cosine sine term. These are displacements. Now, and then we solved also an example problem. We talked also about symmetry in structures. We finished here. So today, let's look at this potential energy approach in finite element formulations of a bar. This is a bar. We are going to look at how variational method or principle of minimum potential energy can be used to solve for displacement or stress or nodal loads here for this bar. We already solved this bar problem for the case where we had two forces at the nodes. But let's look at this in more general and more powerful method of doing this. So today, a little bit at the beginning, a little bit patience going through this formulation, but this is very important. This variational method in general, it is very, we get a lot of information from this procedure. It's much more powerful than the direct procedure that we did before. That direct procedure was easier to follow. This one a little bit more involved, a little bit more patience at the beginning especially, and then we will apply this and we will appreciate what it does for us. All right, so a little bit we are going through the formulation. I will try to make it as easy as and not also spending a lot of time, but you can look at this more in very detail yourself. This is one bar, very simple, one-dimensional bar. Two nodes, node 1, node 2, x-axis here. So we put this x-axis goes from node 1 to 2. Length of this bar is L. Now this bar is subjected to three types of loadings. One is axial force, concentrated force at the node. Concentrated force at node. So F1x, this is concentrated at node 1. F2x, concentrated at node 2. This is one type of force. Another type of force is this one called X sub B, body force. This is called body force. This is force per unit volume. This is for the case if we want to include the weight of this structure. This is weight of this structure. If we want to use, then this is the density, force per unit volume, body force it is called. And another type of force, traction, T sub x here, it is surface force. This is force per unit surface area. So three types of forces: nodal forces, or concentrated forces; body force, force per unit volume; traction, force per unit area. Three types of forces are involved here. Let's see how we can find displacement, stress, and nodal load subjected to, again, body force, X sub B, this is this one, and traction. Now, we are going to use the very powerful technique, principle of minimum potential energy. Now, what does it say? This principle says that if a structure is in equilibrium, its potential energy is minimum. If it is in equilibrium, its potential energy is minimum. So let's write the total potential energy of this bar subjected to these loadings and make sure that it is minimum. Minimize it means we put the derivative, find the derivative, put it equal to 0 to find the minimum or maximum of a function. That's how we do this. So total potential energy is given by this U plus omega. U is strain energy. You have it from strength of material, from your stress analysis course. U, strain energy or energy of deformation. When a structure deforms, it is like a spring. It absorbs some energy. So this is one energy. Another energy, when you apply these loads to this structure, this load deforms this. So this force does some work. There is some potential energy due to this. There is some potential energy to this force. And there is some potential energy due to this force. Adding everything together, that gives total potential energy. This must be minimum according to this principle of minimum potential energy. Our job would be a little bit, a few minutes, just patience going through these derivations, substitutions, a little bit manipulation of these formulas, and then derive what we want. Let's start with U. U is strain energy. It is given by this. It is half of integral of sigma x epsilon x. This is actually area under the stress strain diagram. If you plot stress strain diagram, this is straight portion. This area, it is half of this base times this height. So half of sigma times this epsilon. It is actually this one, half of sigma times epsilon. Times, but it is per unit volume. So multiplied by dV, integrate over the volume. That is U. Now, omega here is due to three types of forces, this one, and this one. So in order for each one, for concentrated nodal forces, it is actually F1x U1, F2x U2. U is displacement in the x direction. So it is F1x times U1 and F2x times U2 displacement of this. You can write it in a summation form like this. Negative. Now, traction. Traction is force per unit area. This is force per unit area times area ds. This is differential area. Force per unit area times area is force. Force times displacement. U is displacement. That gives work. Negative of work is potential energy. The same for XB, force per unit volume. Times volume is force. Force times displacement is work. Negative of work is potential energy. So these are the terms that we need. A couple of notes here. Strain energy is the area under the force deformation diagram. Strain energy density is area under the stress strain diagram. And potential energy of an external force is always opposite in sign from the external work expression. So potential energy always negative of work, because potential energy of external force is lost when the work is done. So it is always in the negative direction of that. So put everything in the total potential energy, it is, and then making some substitutions here. This is a dV. For dV, we can write cross-sectional area times dx. This is this bar. So differential volume of this would be just cross-section area times dx. So this is this one, ADX. So if we do this, we find this to be this area, this A over 2, and then sigma epsilon. This is stress, strain, times dx minus this one is F1x U1, F2x U2. This is force times displacement at nodes. This one traction times this one. I just brought this U here. So this is just the same formula. I didn't change any, make any changes. It's just U is brought to the front. And the same is the same as this one. It's just U is here. So we need to make some substitution. This asterisk means need substitutions. So for sigma, epsilon, and U, I want to make some substitutions. Epsilon, Well, it is simply derivative of displacement with respect to x, or in difference form, we can write it like this, or in matrix form, we can write it like this. This one, we call it a B matrix. It's just a definition of this B matrix, negative 1 over L, 1 over L, B matrix. And this is the displacement vector. These are displacement at nodes. So epsilon is BD. This is this. But we know that B, it's defined, just the definition for B is this. Now that we have epsilon, let's find stress actually here. Let me jump to this one. Stress is E epsilon. In this class, we represent everything in matrix form because these computer programmers need to know, call these matrices by name. So we call this one D matrix. It is the material matrix actually. So all materials go into this matrix. So in this case, it is just simply E, modulus of elasticity. But let's call it D matrix. And this epsilon, it is simply BD. So it's BD. So sigma is what? DBD. Sigma is DBD. That's what we wanted to make this substitution for sigma outside this here. Now, U, remember here also we want to replace U, substitute for U. U is ND. Can somebody tell me where N is this? Can somebody tell me what N stands for in this class? N stands for what in this class? Question for you. Anyone?
The shape function?
Agree with your friend, anyone?
Yeah.
You're right. It is a shape function, and we use, remember, let me go back quickly here. And that was where we derived this, you see, for this bar is one element, and this, we said that this N1 and N2, we call this one shape function here. These are shape functions. So U is N1, U1, N2, U2. This is this one. And this is our N matrix N, and this is D. So for U, we are making this substitution here. This is U, which is ND, where N is given by this. So putting everything back now into the equation for total potential energy, it is A over 2. This is this one, you see, it is A over 2. We need to make this substitution for sigma and epsilon now here. To make this multiplication possible, we have to write it as sigma transpose times epsilon, because we have it in, these are all in vectors, column vectors. So we transpose it to make sure to be able to multiply it by epsilon. So this is sigma transpose epsilon. This is D transpose times P. This is a vector which contains nodal concentrated forces. And these are the two terms for traction and also for body force. If we do this one, now for sigma transpose, this is sigma, we said it is, this is sigma. It is DBD. Transpose of this, it is D transpose, B transpose, D transpose. This is here. D transpose, B transpose, D transpose, and times another epsilon. Epsilon is BD. It is BD. This is our strain energy. This is D transpose P. Keep it the same. This one it is. Now, U we can write it as ND. U is ND. N is shape function. So write this one as U is ND. Transpose of this would be D transpose N transpose times T. The same U transpose, it is D transpose, N transpose. And this is the body force here. We can now write this in this form that, you see, these are not functions of X, nodal displacement, or this B matrix. This is B, just simply it is negative 1 over L, 1 over L. So it's not a function of X. This is material models of elasticity. So these are not functions of X. Everything comes out as what you see here. All of these terms come out of this integral sign. And integral of dx is simply L. So this is L multiplies by this. So this is the whole thing here. And you see this, there is D transpose here, another D transpose here, another D transpose here. Factor them out. Take them out. So it is negative D transpose times F, where this F is now given by this here. You see, this F is now consists of, we are factoring this out here. So this would be this P, this one, factoring this transpose out. So this would be integral of N transpose TDS, it is this one. And this last term, factor this out. So it would be integral of N transpose XBDV, this one. That this formula is very important. Keep in mind, we will come back to this, we need this one. So now this is the very important formula. We need to minimize, principle of minimum potential energy. We have to minimize this. Derivative of this with respect to displacement is this one. Derivative of this with respect to displacement. This is displacement transpose, this is displacement. Derivative of this simply is ALB transpose DB. This is this one. It is A times L B transpose DB. This is this one. Times D negative F is equal to 0. This is F, you see, this is D transpose times F. Derivative with respect to this is out, so this F remains. It is negative F is equal to 0. In other words, something, this something here multiplied by D is equal to F. Take it to the other side, it is equal to F. This something is called element stiffness matrix. That's what we wanted to find. Therefore, element stiffness matrix is this one. It is ALB transpose DB. This is this one. Now, for one-dimensional bars, what do we have? This K is A times L, length of the element, B transpose, it is negative 1 over L, 1 over L. Remember, this was B here. B is where we defined this B. This is B here. This is negative 1 over L, 1 over L. So transpose of this, it is this here. This is B transpose. D, it is our material matrix. It is modulus of elasticity. And this B again, this is our B. That's it. If we multiply these terms, we get this. Does it look familiar to you or not? Anyone? This one, familiar or not?
Yeah.
Yeah.
It is what we had before. Very good. You're right. It is what we had before. This is AE over L1 minus 1 minus 1, 1. It is actually, let me quickly go back here. Yeah, this is this one actually. It is this one, AE1 minus 1 minus 1, 1. It's for this bar when it is subjected to this tensile force. So we got the same thing, but in addition to this, we got some more important items by this variational method. So this is same as K that we derived before, but in addition to this, we found something more importantly, this one, this F. F consists of concentrated nodal forces, traction, body force. Let's now apply this, see what we gain from this variational method, which is the most powerful technique actually in finite element formulation. So let's see what we gained here. Pay attention to this example problem. Example 1, I will do this one, explain this one. Example 2, you are going to do it yourself by hand. So pay attention to this. If you have questions, you have to let me know, because next one, you are going to do the other one. Now, what you see here is one element, node 1, node 2, length L, distributed force applied to this, linearly varying. So this traction, it is in the form of force per unit length, although traction we said force per unit area, but it doesn't matter. This is just, we can also express this in force per unit length. If it is force per unit length, you multiply it by dx instead of ds. So this traction is varying like this, cx. This is, c is a constant. So is a constant, but x, when x is 0, it is 0, and it varies linearly like this. So this is a type of load on this one. The question is to find the equivalent nodal forces. What you see is distributed load on the element. Finite element methods doesn't like this behavior. Our formulas are written for nodes. So these forces must be applied to nodes, not like this, distributed. You enter it to Phi-map. Phi-map inside converts it into nodal forces, concentrated forces at nodes. So here, our goal is to get rid of this distributed load, apply equivalent forces at these two nodes. How do we do this? Well, we apply this formula that we learned today. F is equal to P plus this due to traction due to this force. This is the one that we learned today, this one, it's the same. So how do we apply this? Well, in this problem that you see here, let's see what happens to this formula. This term represents concentrated nodal forces. In this problem, do you see concentrated forces at nodes? Yes or no?
No.
No, there are no concentrated forces, so this out. This one represents body forces. It is due to weight, for example, it's like density of a structure, if we want to include weight of a structure. This force per unit volume. In this problem, do we see any force per unit volume anywhere? No, there is no force per unit volume. It's not weight or anything. It's just force per unit length. It is just this one. This is traction. There is a force applied, but instead of a force per unit area, it is per unit length. It doesn't matter. It's a surface or force along the length of this. So we don't have this one. We have only this one. This F actually represents this F1x, F2x. This is nodal forces. Force at node 1, force at node 2. Shape functions, 1 minus x over L, x over L. Is transpose of this shape transpose. We looked at shape functions. It is 1 minus x over L, x over L. Traction, it is this one, Cx. But instead of here ds, it is just simply times dx, but integrated x varies from 0 to L. Just simple integration here, just multiply this by this. integrating, this is CL squared over 2, and this would be the same, similar to this, and integrating this and simplifying, we get this. Now, total force applied to this bar is what? Total force is area under the load diagram. This is our load diagram. Total force here is what? This is Cx, so this would be Cl here, times L divided by 2. So this is Cl squared over 2. Total force is Cl squared over 2. So the one forces that we found, nodal forces, it is this one, which is 1/3 of this, and this one, which is 2/3 of this. So in other words, these two forces, it is this one, which is 1/3 of this total force, and this one, which is 2/3 of total force. So what does it mean? Graphically, you can see it here. It means that this was what we were given originally. Force was distributed along the length of this. When x is 0, there was no load, and varies to a maximum like this. This is the traction. We said that finite element method doesn't like this distributed load. We need to find the equivalent concentrated forces, like this one. This, we said that at F1x is 1/3 of total force. 1/3 of total force applies at node 1, and at node 2, 2/3 of total force. This would be 2/3 of total force applies at node 2. So we are given this one, phi map inside very quickly converts it to this one. Now we can work on this one because this force is now concentrated at nodes, and then we can now proceed with this form. All right, so that's how we find the equivalent nodal forces. We use the formula that we derived today, and we find the equivalent nodal forces to be like this. That's what we like to see. All right, any questions about this problem?
Professor, can you give me a real life example of a varying traction force?
A varying traction force. You see, this one, suppose you when we insert like a nail actually, or a column into a, for example, seabed. In seabed, actually, we hammer these columns, these posts, then we can put the, for example, harbor, the TJT or the harbor on this. So these poles that we insert into seabed, for example, behave something like this. At the bottom, the force is very large, and at the top, it is very small. So actually, a behavior similar to this. You can see another example, you can see the drilling. In drilling, for example, for oil, gas, or water, also from underground, these wells are sometimes in the order of 2, 3, 4 miles or more. So this pipe that we use to drill, we apply a torque here, and then at the bottom. So actually, in this case, it is like this, that we apply the torque here just very rough estimate, but that's for torque, of course, it's not axial. For axial, as I said, the model would be just like a post which we insert into a seabed. But similar to this one, if it is torque, you can see that torque that we apply with the machine up, the pipe comes in contact with soil. So at the bottom it is less, but at the top, a lot of torque is applied to this here to overcome the resistance from soil, from underground. So you can give this example like this. But again, the second example I gave you was for torque, not for axial load. All right?
Yeah, thank you.
Sure. Now, any questions about this? Because I want you to solve the second problem. Any questions on this? Again, remember, distributed load, linearly varying. Now, to do this one, we use the formula that we derived, and then we use the shape function. These are shape functions. We put it here, and then we saw that the equivalent of this is that 1/3 of the total force goes to this node, and 2/3 of the total force goes to this node. Now, similar to this problem is this one, but in this case, this is actually a simpler one. That's what I want you to be ready to solve this one. You have your paper and pencil ready?
Yes, sir.
All right. Now I want you to make a sketch of this one. This is a uniformly distributed. It is just force per unit length. It's not varying, so simpler. Force is distributed along this length. I want to find the equivalent of this. What force applies to node 1? What force applies to node 2? Very practical and very important. That's the goal for this uniformly distributed load. What are the equivalent forces at these nodes 1 and 2? Make a drawing of this one and write this formula. Write this down. So you are familiar with these parameters, these terms involved here. All right. Now, we see that in this problem, there are no concentrated forces at nodes. At node 1, there is no concentrated force. At node 2, there is no concentrated force. So this is out. This is body force. There is no body force here. This force per unit volume. There isn't anything. This is due to weight, due to an inertial force. This is due to centrifugal force, due to electromagnetic force. So, but we don't have it here. The only one we have is here. Our traction here is this one, just simply Q. I want you to use this one. Very similar to the steps that we did here. Follow the same steps here. Tell me what are the equivalent nodal forces at nodes 1 and 2. That would be your job, 2 minutes. Follow the same steps. Tell me what are the equivalent nodal forces. Follow the same steps, 2 minutes. All right. Anyone want to share with us what you got for the equivalent nodal forces?
I just got 1/2 at node 1 and 1/2 at node 2
1/2 of what?
of force
Which
or
is
Q.
1/2 of Q. So what did you get? What did you get for equivalent force at node 1?
It's 1/2 force, which is Q times length.
Anyone agrees with your friend?
Yeah, I agree.
I agree.
You're right. Very good. This is the formula that we use. We said that we derived this one. This is F. This F is actually F1x, F2x. Shape functions, this is this one. Traction, simply in this case, it is Q, but this is force per unit length. It is not a function of X. So just simple multiply this by this and integrate and add QL over 2, QL over 2. So yes, actually, but the total force is QL, this force per unit length. So total force is QL. So half of total force applies to each node. So actually what we are given, uniformly distributed load, it is actually like this. It should be half of total force goes to node 1, half goes to node 2, half of the total force. All right. Any questions on this before looking at another example problem? Any questions on this? All right. If not, let's look at another example problem from our textbook. This is a problem 357, very similar, closely related to this. This is a bar hanging from the top. This has a length of 60 inches. It is hanging like this. Determine the nodal displacements using 2 equal length elements and in part B 4 equal length elements. Now, this is subjected to its own weight. So it has weight. Its cross-sectional area is given, modulus of elasticity is given, and weight density is 0.283 pound per inch cube. We use sometimes gamma or rho W for weight density, or gamma, either one that we use, the notation. We want to use the potential energy approach that we learned today. We cannot solve this without by direct stiffness method, by direct formulation that we did before, because now there is weight involved here. This weight is force per, we know the density here. So this is force per unit volume. So it involves the body force that we discussed today. So we want to see what is the deformation nodal displacement when we use 2 equal length elements or 4 equal length elements. We are given A, E, and gamma. The procedure is, first item is this one. This is this bar. Its weight is distributed like this one I have shown, like this. It has a length L, so to divide it into 2 elements, it would be node 1, node 2, node 3, and it would be L over 2, L over 2. Total length was L. Now, this would be, we can write it in terms of force per unit length as gamma A. Gamma is force per unit volume, but if you multiply it by the cross section, then gamma A would be force per unit length. So this is force per unit length distributed uniformly, like the problem that you solved right now here, actually. This force distributed uniformly, the same as this one now. This force is distributed uniformly at node 1 and at node 2 and node 3. So total force here is what? Can somebody tell me what is the total force of on element 1? This is element 1 from node 1 to 2. Total force is what here? Because we said that half of the total force should go to node 1, half should go to node 2. We cannot carry it like this when it is distributed. Phi-map has to convert it to equivalent nodal forces. So this one we have to get rid of, but we need the total force, then put half at node 1, half at node 2. What is this total force here? It is gamma A times
L over 2.
times L over 2, then half goes to this node, half goes to this node. So gamma A L over 4 goes to node 1, gamma A L over 4 goes to node 2. This is for this element now. Go for element 2. For element 2, the same thing. Gamma AL over 4 goes to this node, gamma AL over 4 goes to this node. So it adds it to the previous one, makes it gamma AL over 2 for this node. So that's what intermediate nodes always carry twice the load at the boundaries compared to those at the boundaries. So this is where you see, because this is common from this element and this element, so it takes half from each side and makes it gamma AL over 2. So with this model, now we can proceed. Force is now applied at each node. We can proceed with this one. This is a bar subjected to axial loading, so you know that is AE over its length, but length of this, in this case, it is L over 2, 1 minus 1 minus 1, 1. That's it. We have to apply it for this bar now. Somebody tell me, what is the size of the global stiffness matrix for this problem? I need to create the global stiffness matrix. What is the size of the global stiffness matrix?
3 by 3.
Why 3 by 3?
Because
You're
there are
right.
3 nodes.
And 1 degree of freedom per node. Very good. You're right. So let's now, this is AE over its length is L over 2. So this would be 3 by 3. This is the global stiffness matrix. This is a system of equations that we have. F1x, F2x, F3x. Apply the boundary conditions at node 3. This is node 3 here. This is fixed, no displacement. So this is a homogeneous boundary condition. Row and column out. Force boundary conditions, F1x, F2x. This is what we have. F1x, it is gamma AL over 4 and gamma AL over 2 at node 2. This is this one, gamma AL over 4 and gamma AL over 2. There is negative here because this is a downward. So when it is downward, put negative. And that's it with these two equations, two unknowns. These are the displacements. Gamma L squared over 2E. If we plug the numbers for gamma, gamma is this, length is this. These are the displacements of node 1 and 2. It is this. Now let's do 2 more items. Let's use this displacement. Let's compare it to the exact solution. Let's find the exact solution and compare. Exact solution is like this. Exact solution, if you consider this from your strength of material, you had it in your ME2 and ME191. If you cut it at the section here, at the distance x from here, total force here is P times X. P times X times dx here. In this case, it would be a gamma times AX. Gamma A is the force per unit length times X. So this would be the total force applied at this section. This is P as a function of X here. So the total force that applied at this one. So it is gamma AX dx integrated from 0 to X. It would be this one. Now applying boundary conditions, when X is 0, we are measuring X from here. So when X is L, displacement is 0. So here put X is L, displacement 0. If we do this, at XL displacement 0, 0 is put XL here. We find our constant of integration here, and when we plug it back into this one, our displacement is this. Displacement is given by this function. Yeah, using the numerical values for when X is 0, this is at node 1. And when X is 30, at node 2, we get these two numbers, this one and this one, at node 1 and at node 2. Compare it to what we got here. Let's see, at node 1, we get negative 16.980. This is the same as this one. So finite element solution, and this is the exact solution. Same. Our finite element solution matches with the exact solution. Remember, at the beginning, we said finite element method is an approximate method of solving differential equations and in physics and engineering. But it matches the same as what we get from exact solution. Let's plot them. This is the plot. If this is the bar, node 1, 2, 3. X is 0 here, L over 2L. If we plot this deflection at node 1, at node 2, and at node 3, it is 0, of course. Finite element solution is like this. If you draw a straight line from this node to this node, straight. And the same straight here. That is the finite element solution. Now, from here, if you draw a curve like this, we saw that at node 1 and 2, the finite element solution and exact solution, they match. So actually at this node, we have the same solution. But of course, if you interpolate at other locations, finite element method, you use a linear function, therefore our variation is like this. But at nodes, it matches with the exact solution. That's what we wanted to see. Finite element gives exact solution at nodes. In many problems, actually, finite element methods matches with the exact solution. All right, any questions? We finished with chapter 3. That was the last discussion on chapter 3. Any questions? All right, if no questions, we are done with this one. Let's now talk about beams. So we were actually, this is module 7. We are here September 27th, beams. So let me click on this one and start our discussion on beams. Now, what you see here, 3 types of beams. Their job is to carry transverse load. So beams carry load which is perpendicular to this or at an angle. If it is perpendicular to this, so it doesn't produce any axial force in this, but if it is at an angle, it produces axial force. But if it is perpendicular, it would be just what? Bending and also transverse shear. 3 examples. This is a simply supported beam. Pinned, roller. Cantilevered beam, fixed at this wall, free at the other end. And this one, it is overhanging, pinned, pin. I'm sorry, this is pinned, and then here we have a roller. So this is overhanging. To solve this beam problems, in general, we have two theories that help in this process. One is Euler-Bernoulli, one is Timoshenko. Euler-Bernoulli considers deflection due to bending only bending. But we know that at any cross section we have a moment and we have a transverse shear. So there is a deflection also due to shear. This one neglects it, Euler-Bernoulli, neglects the effect of deformation due to shear. But Timoshenko considers this. In Timoshenko theory, we will consider both the effect of bending as well as shear. All right, so two theories we are going to use to analyze beam problems. You used it in the lab 2 weeks ago, actually, for beams. Now let's look at how we do the finite element formulations for beams. This is a beam element that you see here. Always when you have questions, feel free to ask. Be active in your learning and feel free to discuss. This is a beam element, node 1, node 2. This is our x-axis, this is our y-axis. Displacement in the y direction, it is called v. Displacement in the x direction, it is called u. Now, at any cross section, we have a transverse force F1y at node 1. There is a force F1y. Associated with this force, there is a displacement V1, which is displacement in the y direction. And also there is a moment M1. Associated with this moment, there is a rotation phi1. Do the same thing for node 2. There is a force F2y, displacement V2, and a moment and rotation associated with this. This is our model in finite element methods. How many degrees of freedom? Anyone can tell me? How many degrees of freedom do you see here?
2.
What are they? You are right. What are they?
V and M.
V and not M. M is a load. But degree of freedom, these are displacement or rotations. So it is V1 and phi1. Phi is rotation. Very good. So we have 2 degrees of freedom per node. And how many nodes does this element have?
2.
2. So 2 nodes times 2 degrees of freedom per node makes it 4. So our stiffness matrix, element stiffness matrix should be 4 by 4. All right, to do this problem, this is our notation in finite element methods. This is our notation in finite element methods for force, upward positive, and moment counterclockwise positive. But our sign convention in solid mechanics is like this. If this is a differential of this beam, if this V is downward, positive, and moment counterclockwise like this, or on the other side to make it in equilibrium, so it should be in the other directions. But this, everything here, what you see is positive. But if you, in the opposite direction, everything here is negative. This V is downward, positive, now upward, positive. Moment counterclockwise, moment clockwise, similarly to this one. So everything here is positive, everything here is negative. So I have a question for you. I have a few questions. This F1y in finite element methods, positive upward. In solid mechanics, is it the same or not? F1y, compare it to this one. In solid mechanics, is it considered positive or not?
Yes.
You're right. Look at this one, it is positive upward. If you look at this segment on the left side of this one, it is positive upward, so this positive upward. So yes, in solid mechanics, it is also positive. Now look at the moment. Counterclockwise positive. In solid mechanics, is it positive or negative?
Positive.
Positive. Anyone agrees with your friend or anything else?
Yeah, I think it's positive too.
Well, it is not positive. Tell me why it's not positive. Look at this one. This is counterclockwise. If you look at this one, this is clockwise. This is counterclockwise. It matches with counterclockwise here. So this one in finite element methods matches with this one, negative, in solid mechanics. Now let's look at this one. Tell me, this force upward in finite element methods, positive. In solid mechanics, is it considered positive or negative?
Negative.
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 Because this one, if you look at this one, it doesn't match with this one. It matches with this one. This is upward, this is upward. So this is negative, you're right. So this F, which is positive in finite element method, it is negative in solid mechanics. Now, moment, counterclockwise. It is what?
Positive.
Positive, very good. It is the same as this one. So it matches with this. Okay, so this is our model in finite element methods. This is our model in solid mechanics, but they don't match. Sometimes we saw that they are in the different direction. So let's use Euler-Bernoulli. We said that Euler, there are two theories. So we use this one, Euler-Bernoulli beam theory, and we will consider effect of only bending. We neglect the effect of this shear, and then later we use Timoshenko to take care of that one. To do this, we follow the same procedure that actually we did before. We start always with an approximation function or a displacement function. Start with V. V is displacement in the y direction. It is given by this cubic equation. A1, A2, A3, A4, these are constants. We need to find them by applying boundary conditions. Our boundary conditions are when x is 0, look at this one, this is x. When x is 0, displacement is V1 and rotation at this node is phi1. When x is L, This is L. When X is L at this node, our displacement would be V2 and rotation would be phi2. That's what we are doing here. When X is 0, this is 0, 0, 0. So our V would be equal to A4, which is V1. Derivative of this is rotation. So rotation is dv over dx at x is equal to 0. This one would be 0. A3 is equal to phi1. When x is L, put x is L, xl here. So it is A1 L cube plus A2 L squared plus A3 L. It is equal to, when x is L, it is V2. And finally, rotation, when x is L, it is phi2. So find the derivative of this with respect to x and evaluate it at x equal L. It is equal to phi2. 4 equations, 4 unknowns. We can solve for A1, A2, A3, and A4 and plug them back into this equation for V. We get this one. Very important formula here. This is the equation for V. These are nodal V1, V2, these are nodal displacements, and phi1, phi2, these are rotations. Now, like what we did before to find the shape function, we did it before. We can write this one in this form. It is N1, N2, N3, N4, and D, the same as what we did for the case of line element, linear line elements. That was for a bar subjected to axial loading. But for this case, it is now for beams, it is like this. If we write this, we find the shape functions N1, N2, N3, N4. These are shape functions. These are given by this N1, N2, N3, N4. These are shape functions like this. Tell me, what type of equation is this one? Here you see this. This was the where we started with, displacement function. What type of equation is this? It is a
Cubic?
Cubic.
a polynomial of order 3 or a cubic equation. Okay, very good. What type of equation is this?
The cubic as well.
Cubic again. So again, you start your approximation function or displacement function to be cubic. You end up with shape functions which are cubic. If you started with quadratic, you end up with quadratic. And if you start with linear, like what we had before, we had linear, then we ended up with linear. These are the shape functions for beam problems, for beam elements. They play an important role, and in future we will see that that they are very important in our finite element formulations. Now, our goal is to find the element stiffness matrix. Always we want to find the element stiffness matrix, because if we have it, then we put them together, create the global stiffness matrix, and then we can solve for displacements and rotations and everything else. To do this, we use these two equations from strength of materials. In strength of materials, we learned these two equations, which are very important actually. Moment is related to EI is modulus of elasticity and area moment of inertia. Second derivative of V with respect to X. And V is EI, third derivative of V with respect to X. So now based on this one, let's apply this to find V1. V1, remember at the beginning you told me that V1 here, F1y, You said F1y is the same as V here in solid mechanics. So F1y is the same as V. It is here. F1y is the same as V, but V here is EI third derivative of V with respect to X, but evaluated at when X is 0. So 3 times derivative of V, but we found V. This is our V. This is X cubed. This is X squared. This is X here. So we need 3 times derivative of this and evaluated when X is 0. This is this one. 3 times derivative of this V, when put X is 0, we get this one. EI over L cubed, 12V1 plus 6L minus 12V2 plus 6L2. Do the same thing for others. Also M1. Remember, in finite element method, M1, here it is like this, counterclockwise. If we look at this one, we say, no, it doesn't match with this. It is this one counterclockwise, so it is negative. So M1 here is negative M here. If we do this, this is what you see, M1 is negative M, but M is second derivative of V with respect to X, and evaluated when X is 0, we get this one. Do the same thing for F2y. F2y here, F2y is this one. It matches with this one. So this, I'm sorry, this one matches with this one. So this is negative. So F2y is negative V. This is this one. F2y is negative V, but V is third derivative of V with respect to X, but evaluated at XL, when X is L, we get this one, and finally also moment at node 2, we get this one. Let's write everything in matrix form. All of these 4 equations. This is F1y, M1, F2y, M2. This is F1y, M1, F2y, M2. This is this. And these 4 equations, you see V1, V1, V2, V2, and it repeats again, V1, V1, V2, V2, and here in matrix form, we have it like this. This is our force vector, this is our element stiffness matrix, and this is our displacement vector. That's what we always want to see. Something multiplied by D is equal to F. This something is called our element stiffness matrix. This is EI over L cubed and multiplied by this term. Now, question for you. Is it symmetric? Is this matrix symmetric or not?
Yes, it is symmetric.
Yes, it is symmetric. As what you see here, this is 6L, this is 6L. I'm marking this term that you should see, for example, negative 6L, the same negative 6L. You see 2L squared here, it is 12 squared here. It is negative 6L, negative 6L. So yes, it is symmetric, and it plays an important role in finite element methods. Symmetry reduces the size of these matrices. Remember that this can be, let's say, 1 million by 1 million, the global stiffness matrix, of course, not the element stiffness matrix, but from this one, we create the global one, but the global one is also symmetric if it is symmetric. And it reduces the number of equations because the global stiffness matrix can be 1 million equations, 1 million unknowns, but if we have symmetry, then it reduces the number of computations to a very large degree. Now, one more item here, you see, remember, we said that there are two types of beams, Euler-Bernoulli beams and Timoshenko beam or Timoshenko theory. This one, Euler-Bernoulli, does not include the effect of shear, but Timoshenko includes the effect of shear. Now the question is, when should we include it, when we don't need to include it? Well, rule of thumb, by definition, a beam is defined when this long, slender beam, it means when it is very long compared to its height. By beam, we mean that this length is actually at least 10 times its height. If this cross-section is rectangular, and this beam is 10 times its height, the effect of this shear is just simply, the effect of this is just 3% of the effect of bending. So effect of this is just very small compared to this one. If this length is 8 times its height, and if it is rectangular cross-section, then the effect of this shear is just 5% of the effect of this. If this 3% or 5% is not a big deal, just we can neglect it and then make it simpler, make our life simpler, and do not include the effect of shear. That's what this note is talking about. Let's see. A general rule for rectangular cross-sections, for length at least 8 times the depth, transverse shear deflection is less than 5% of the bending deflection. So we can neglect this effect of this transverse shear. It's not significant, for example, if it is 5%. If this was 10 times the depth, then the effect of this was 3% even. So the longer it has, the longer the beam is, the less the effect of this transverse shear, deflection due to transverse shear. So we can neglect this one. That's what Euler-Bernoulli is about. If it is a long beam, then we consider neglecting the effect of shear and then make it use this one. Otherwise, we will go ahead and use the formula for the Timoshenko one, which is more accurate one. All right. Next step is to look at an example problem. Any questions? Anyone? All right. If no questions, I don't want to start with this one. I think we covered. I don't want to go too far. Also, we are fine. I stop here. I don't want to. We cannot finish it. I don't want to not complete this discussion. So we will look at this example problem next week, but this week, Wednesday, we will have our activity. The activity will, last week we did frames. So this week we are done with these line elements. We used them for trusses, we use them for beams and frames. We are done. We will switch to continuum elements and analyze a plate problem, a two-dimensional plate problem. We will use triangular and quadrilateral and rectangular elements. All right, so that would be for Wednesday activity. Again, one more item, our quiz is graded and the results are, you can look at Canvas to see what a small note whether what the error was, but solve them again because the procedure we continue. Trusses are simplest, but we continue the same procedure for developing and solving other more advanced types of structures. All right, everyone, I stop here. If no questions, have a